Hello everyone, today I'm going to share some of the thought in my teaching life. Something to do with Heron's formula. As a math teacher, whenever I introduce Heron's formula, I want students to practice it right away. To compute the area of triangle from its three sides. I also want a good example, integer sides and an integer area. So checking word is easy and satisfying. I thought about a simple method for any teacher can use. Let's build a beautiful Heronian triangle that has integer side length and integer area. The Heron formula is as shown below. Area triangle with side ABC equal the square root of s minus a, s minus b, s minus c, where s is half of the perimeter. With using the formula triangle 3, 4, 5, then we know that the area is equal to half 3 and 4, and that is 6. This 3, 4, 5 triangle is a good example, but it is too trivial. So instead of this, we can have two copies of 3, 4, 5 and glue them together along the common side 4. So now we have 5, 5, 6. And obviously, the area here equals to double of the previous area 6. So it is 12. And we can also change a little bit by gluing the side 3 instead of 4. And now we have a triangle 5, 5, 8 with the area as 12 again. Now before I introduce this method, if we ask for which triangle has bigger area for 5, 5, 6 and 5, 5, 8, I guess first who see this question may not get the correct answer. Now take another two triangle. So from 3, 4, 5, we can have 9, 12, and 15. And we can have another triangle with 5, 12, 13. So the common is 12. So if this is 9, 12, 15, and the other one is 5, 12, 13, then we have another Heronian triangles with the side length 13, 14, and 15. Which is easy to remember because instead of 3, 4, 5, it is 13, 14, and 15. And the area, of course, will equals to half 12 and 14, that is 84. Or you can use the Heron's formula, s equals to half of 13, 14, and 15, that is 21. So the area is square root of 21, 8, 7, and 6. 21 is 7 and 3, and 8 is 8, 7 is 7, 6 is 3 and 2. We will have 7 times 3 times 4, that is 84. Using the same two triangle, instead of taking 9, 12, 15, we can actually cut off the 5, 12, 13, and this left with a 4. So meaning that 4, 13, 15 is also another Heronian triangles. Of course, the area will now equals half 4 and 12, that is 24. So in conclusion, it is either glue along a common height or cutting out the smaller triangle. So in general, if there is a triangle 1 with side length x1, h c1, and triangle 2 with x2, h c2. So we can have two triangles from here, that is x1, x2, and c1, c2. So that would be x1 plus x2, c1 and c2. Or suppose c1 is greater than c2, then we cut away the c1. So then this is h, this is c1, and this is c2. So this is x1 minus x2. So what we left will be c1, c2, x1 minus x2, provided that c1 greater than c2, meaning that x1 greater than x2 for the general case. Now look at these two Heronian triangles, 6, 8, 10, 4, 13, and 15. So the area for the first one is obviously 24. For the second one, it is actually come from 4, 5, 12, 13. And again, this area equals half 4 and 12. That is also 24, meaning that we can have two different Heronian triangles with equal area. Another examples, 9, 10, 17, and 3, 25, 26. Both have the area equals 36 because there is 8, 6. And for the other one, 7, 24, 25. So they are from the triangle 6, 8, 10 being cut from the triangle 15, 8, 17. And for the other one is 7, 24, 25 being cut from 10, 24, 26, which actually original from 5, 12, 13. That also give another question that all such triangle can be cut into two triangles where both also Heronian triangles. And the answer is obviously no. Take for an example, 5, 29, 30. We can calculate the S is half of 5, 29, and 30. That is 32, where the area equals square of 32, 27, 3, and 2. And that would be 8 times 9, and that is 72. If it's 72, it means that this height is equals 144 over 5. But we can enlarge this triangle 5 times so that this is 25, 150, 145, and this become 144. After calculation, that will be a 17. So meaning that the triangle 17, 144, 145 being cut from the triangles 42, 144, and 150, which originate from 7, 24, 25. So next time you teach or learn Heron's formula, don't stop at one example. Start from familiar right triangles, glue along the common height, or cut away the smaller triangle, and you will uncover a whole family of integer side, integer area triangle. Now there's a challenge for you. Among all Heronian triangles with area 120, which one has the largest perimeter? Give me your answer in the comment. That's all for today's lesson. Hope you enjoyed it. I'll see you again next time. Bye bye.